Okay, so here we are, Stats 102B, Introduction to Computation and Optimization for Statistics. And welcome. Great. All right, and so the syllabus I haven't completed, but this is what I've got, okay? We've got homework, a midterm, and final, and then we'll have a forum for you to participate in. I'll take attendance, and then the rest I filled in with some free points here. And I think this adds up to 100. Okay? So the midterm will be week 3 Wednesday, and the final will be week 6 Wednesday. Okay? And there's a total of 6 weeks, and we meet twice a week, and so that's a total of 12 sessions, and that means we only have like 10 sessions if you take out the testing ones, right? So each session's like an entire week of content, and that's really hard to do. I've got an hour and 50, and I'm gonna like try to compress a bunch of stuff. You got discussion section after, which I think Jake will kind of expand on some of this stuff. But anyway, try not to miss class, because if you miss class, that's like missing an entire week of stuff. And some of the stuff in lecture, I'm going to have to kind of go over a little bit faster than I normally would, okay? I'm like trying to trim down some of the stuff I cover. But at the same time, I want to make sure you guys learn everything that you're supposed to learn for the course, and so it's a little bit tough, okay? But anyway, we've got that. Okay, grading. If you've ever taken a class from me before, I go straight scale. I don't curve. I don't like to rank students against each other. The only exception is for an A+. I'll do the top 5% of students will get an A+. That's the only grade I give that is relative to peers, okay? Everything else is straight scale, okay? You'll have homework. Don't submit your RMD files. You're going to knit and submit HTML files, and make sure all the output that's supposed to be in the homework is there, okay? All right. Complicated late policy regarding like you get docked by like the hour and stuff. But anyway, it'll all be detailed out in the syllabus. Okay, this is the textbook that we're using. It's called A First Course in Machine Learning. And unfortunately, it is not free, okay? I try to like to use resources that are free or at least freely available online via the many subscriptions that UCLA has. Unfortunately, this is not one of them, and I haven't been able to find a textbook that I like enough to a free textbook that I like enough. So you gotta get this. There might be something on the internet if you are unethical about obtaining your textbooks. No judgment from me, but this is good, and you can buy it wherever. So this is what we're gonna use. Okay. I'm gonna use CampusWire, and here is the link to join with this code. And I've got some kind of point system to give stuff. Regarding CampusWire, you can post anything from lecture. But a lot of your homework assignments will be code-based, okay? This is part of the 102 series, which really emphasizes writing computer code and R and stuff. And so what I don't want CampusWire to turn into, or any of these few forums to turn into, is people just posting homework solutions and code and things like that, okay? So if it's from the lecture, you can copy and paste that code, okay? But do not post your code online. And as far as answering other questions or posting code, you're allowed to do 1 or 2 lines of code, okay? And if you can't If the thing you're asking isn't within 1 or 2 lines of code, you've got to figure out another way to ask. You can always say, try out this function, or try out this idea, or try out this method, or outline the idea and kind of what needs to happen. That's fine. I just don't want people posting entire chunks of code, all right? We'll do attendance on the online polling tool, and we'll worry about that starting Wednesday, okay? And then integrity, be honest, do your own work, don't copy someone else's stuff, right? Okay, and then a lot of resources. UCLA has a lot of resources for any kind, well, not any kind, but for a lot of different issues that people may face. And so if you encounter anything, and I don't want anything bad to happen, but if something does happen, please make sure you use the resources that are available to you, and don't ever feel like you have to face these issues on your own or by yourself. All right. Again, when I finish the finalized version of the syllabus, I'll post that and that. But I don't know if there's any questions about course policies or anything that I've said so far. So far, so good. Okay. All right. So this is 102B, computation and optimization. Let me see if I can resize this so it's not totally cut off. Oops. Oh, far over. Is that good? All right, there we go. All right. So the way I teach it is it's kind of like an intro machine learning course. We're going to cover a bunch of computational algorithms that have important applications in statistics and machine learning. And a lot of these machine learning methods are optimization problems, okay? Finding the set of values that minimize or maximize a function. The statistics department recently got together to discuss our current curriculum, the 100, 101, and 102 series, to kind of just make sure that the content that we are covering and teaching is relevant and current and all of that. And we meet regularly to try to just make sure that the education you're receiving is good. So at our last meeting, they said they want me. I showed them what I cover and everything. They said they want me to teach more matrices, but they said I don't have to implement the change for the summer because it was we had just met a few weeks back. So so the next time I do 102B, I'm gonna have to add some matrix stuff in there. There's some matrix stuff in here, don't get me wrong, but they want more stuff, more matrix decomposition type things. So anyway, if you don't like matrix decompositions, then this was the right time to take it. So, but anyway, but that's what we have. But I'm happy with the course content we cover, and if you want to learn matrix decomposition stuff, you can always seek that out online. I think there's plenty of resources there as well. Okay, but this is in our current iteration of the class. This is what I'm going to cover. We're going to cover just these key concepts from machine learning, like loss functions and likelihood functions, key ideas like cross-validation and regularization. And maybe you've heard of these things, maybe you already are familiar with a lot of these things, maybe not, okay? And so those are some key fundamental ideas. And then we'll cover some machine learning models themselves, like linear regression. And I know you guys already know linear regression from your 101A class. And then we'll also cover neural networks, some MLE models, all of this stuff here. You guys can read, okay? There's a lot of overlap with 101C. I actually just taught 101C in session A, and there's a lot of overlap. I would say the key difference between 101C and this course is that in this course we really emphasize the computational computer programming aspect, okay? A lot of your homework assignments will require you to code up these algorithms by hand, and you will have to write these algorithms in computer code, and I think there's a lot of educational value in that you will know and be able to explain exactly what's happening when these algorithms run. In 101C, it's a little bit more like we treat these algorithms as black boxes, and we say, here's the data, you apply the algorithm, here's the output that you get, and you don't really have to worry about what exactly is happening on the inside. And that allows 101C to cover a little bit more ground because you're not bogged down with covering the exact nitty-gritty of the algorithmic details. You can cover a few more of these things like random forest and LDA and stuff like that, which we don't cover in our class, okay? So that's what we've got going on. As far as the stats major bigger picture, just to kind of show how this class fits in, we started off with stats 10, and this gave you like statistical inference and foundational thinking, and then we introduced you to computational foundations like writing code. So stats 20 may or may not have been your first exposure to writing code, and then 102A should have cranked up the coding expectations to really expect how much code that you're writing in. So by the time you're in this class, everybody should have taken 102A. If you haven't taken 102A, don't take the class, okay? Because there's already an expectation that we're comfortable writing code, that we can see mathematical ideas and turn them into coding things, and that's what we're doing. The 100 series is all about the mathematical theory, things like, in stats 10 we said you can do a hypothesis test, and that's based on the foundation of the central limit theorem, and the 100 series covers the 100, you derive the central limit theorem and stuff like that, okay? And then anyway, we got 101, the 101, all of this stuff, all right? In the interest of time, I'm going to keep going and stuff, but this fits in. I kind of distinguished the idea that we've got data when it was difficult to collect, when you're like doing an experiment and collecting it. If you've taken 101B, you probably had to do an experiment on the island, and it was probably frustrating to collect that data because it's like every time you clicked a button and you have to wait like 5 minutes for them to drink the Gatorade or something. And that's just a small taste of the bitterness that goes through in collecting data, right? Because can you imagine in a real experiment, you have to meet with these people, like 40 people, and each session takes like a couple hours, and then like people will drop out in the middle of your study, and you're just like, oh, I wasted all this time, okay? And you just got a small taste of that, right? And so you had methods like 101A and 101B where it's trying to just maximize the amount of information you can draw from a small set of data. Okay, 101C and 102B is kind of the flip side. We're now in this information age where we're just generating a bunch of data just by walking around with our phones, and Google's tracking our location and saying like, oh, this is how we know there's traffic on the 405 at this time, although I could have told you that at any day. And so we have these massively large data sets, and prediction is now an important thing, okay? And then 102C, we'll talk Monte Carlo methods, and maybe we'll take that. Yeah, we got a question back there.
Yeah, do I have to be good at graphs?
Do you have to what?
Do I have to be good at graphing?
Do you have to be good at graphing? I don't know what you mean by that question.
Like making graphs in R.
We will make graphs. I don't know what you mean by good. This is a little bit, I don't know how to, I'm sorry, I don't know how to answer your question, okay? Yeah, we'll find out as we go along, okay? All right, data science, okay. I imagine a lot of you are majoring in statistics because this idea of data science has intrigued you. And a lot of companies are dumping money into their data science departments. And it's a double-edged sword. It's good, and it's also dangerous in that now we have a lot of people saying they're calling themselves data scientists, but maybe they shouldn't. And so I argue that data science is, this comes from Drew Conway, who wrote this back in 2013, but says it's a combination of basically math and stats knowledge along with coding skills, okay, and domain expertise, okay? And so by being in the stats department, we emphasize the math and stats knowledge and the coding skills. We're not able to give you any domain expertise because it's going to be different depending on which company you work for, right? If you're going to work for a fashion company, you got to be familiar with fashion ideas. And if you're not going to be a good fit for that company. If you're going to work for a health company, you got to be familiar with the health world, right? And no amount of math and coding skills will help if you're not familiar with the data, okay? There's probably two routes to enter data science. One is through computer science and one's through kind of the math and CS side, right? And depending on which side you're on, will probably emphasize one set of skills more than the other. And so I hope by being a statistics student and you surviving the 100 series that your math and stats foundational knowledge will be strong. If the 100 series were like your worst set of classes, then, well, I don't know. Okay. And meanwhile, people who come from the CS side, their coding skills will probably be stronger, but maybe their math and stats background will not be as strong. And maybe when you work for a company, you'll have people who have come from CS backgrounds and people who come from more math and stats backgrounds. And hopefully, you'll be able to fuse your ideas together and form a complete set of knowledge here, okay? But anyway, both of those are very important. So anyway, you can click this Venn diagram and look at the picture there. Okay, let's get started on content here, okay? And we've got a lot to cover. I've got to gloss over some of the stuff that you're going to have to review on your own time. But we're going to just start off here and say, what is machine learning? And Wikipedia says it's the scientific study of algorithms and statistical models that computer systems use to effectively perform a specific task without using explicit instructions, relying on patterns and inference instead. That is true. I would say, simply we can think of this as we fit models to data. And that's what we do in machine learning. But we have a lot of decisions to make regarding how to specify the model. And but another part is that a lot of the decisions in the model are guided by the data and the algorithm that we use, okay? So whereas in kind of classical approaches to statistics, the researcher is making a lot of these decisions on their own. They're using their knowledge of the subject, they're using their knowledge of the variables and the data being collected, and they make a lot of these decisions. And what machine learning does is it kind of offloads some of those decisions. Of course, you still have to make some decisions, but some of the other decisions can be guided by the data, okay? Like, how many variables do we include in the model? Which variables do we include and not? Some of those can be guided by machine learning, okay? This is a picture of a model airplane, and I just say, a model can be we can think of a model as a simplified representation of something complex, right? So simplified version representing a complex aircraft. And in the same way, a statistical model is a simplified representation of a real-world process that generates data. So in the real world, there's something that generates data, okay? Probably people. So if we're talking about like what products sell on Amazon, okay? So Amazon has all of this data that they collect every time somebody makes a purchase. And what they want to know is like, why did this product sell well and this one did not, right? That's what they want to know. Amazon, I don't know if you guys know or remember, they tried to enter the cell phone market and they developed the Amazon Fire phone, okay? And it was a huge disaster. They invested a ton of money and they made all of this stuff and they had this big thing and it was like, they were hoping to be the next iPhone. Probably 7 people bought it, okay? And it was a disaster, right? And if they understood exactly what people wanted in their phones and stuff, They could have avoided that, right? But anyway, so there's some complex process that goes into what phone you're going to buy next, right? Are you going to buy an iPhone? Are you going to buy the Google Pixel? Are you going to buy a Samsung whatever? Or are you going to buy, I don't know, whatever else is out there, a OnePlus 7 Pro something, this and that. They've got all sorts of stuff. Companies just want to know what drives consumer behaviors. It's complicated. We don't know, all right? So we try to model that, and by saying like, oh, well, brand recognition is important, okay? Or price is important, right? And these are, and it's true for, it's different for every person, right? Somebody is gonna say like, I'm gonna just get this phone because I'm not gonna spend more than $200 on a phone, right? And someone else is gonna say, well, I want the best phone in the world. And I don't know what that is, but so anyway, we're just trying to get a simplified representation that we often represent with variables. There's probably other variables that we can't measure, like what your friends have, right? Because that often plays a role into it, right? Like when you, if you switch from iPhone to something else, your friends will be like, what happened? You're now a green bubble. And I don't know if that plays a role into which product you buy, right? So anyway, this is a famous quote: all models are wrong, but some are useful. And we can use these models that we make to make predictions. And we can use the models that we make to explore relationships between variables, okay? Sometimes one of these goals is more important than the other. Sometimes they're equally important. Maybe we want the predictions more, maybe we want to know the relationships more. Okay, so when you guys get the textbook, all right, and please do get the textbook, and I know students, for whatever reason, don't like spending money on textbooks, and I get it, okay? But I don't know how much money you're paying for this class. It's like a lot, okay? The textbook is a small cost in comparison to the class, and it's worth it. And so anyway, get the book. And we're going to look at some data from the Olympics, where we're looking at the men's 100-meter race, okay? And we just look at how fast was the gold medal time, okay? And we're going to make a simple model. Oh, this doesn't quite fit. But basically, the first one down here, it says like 1896, and this one's like, I want to say 2008, okay? And what we see is that in general, the fastest times have been getting faster, okay? So that's what we see. All right. So here, we might decide to fit a linear model, right? So what we see is that race times have gotten faster. So a linear model, what a linear model means is that the change that happens is constant throughout the data set. So if it improved by 0.05 seconds from 1920 to 1924, the improvement from 2000 to 2004 is also the same. Okay, so we're saying that the rate of change remains constant. That's what it means to be linear, right? And if it's like the rate of change was faster over here and slower over here, then it's no longer linear. So this is stuff you already know, okay? And so when we want to fit a linear model, we've got to figure out the slope and the intercept. That's when you try to draw a line, there's two things that define a line: the slope and the intercept. And so fitting a model is the process of estimating the model parameters. And in this case, we need to figure out how to estimate the slope and the intercept, right? And we want the slope and the intercept that does the best job. So we want the line that does the best job in our data, okay? All right, and so for least squares regression, ordinary least squares, we are driven by this thing called an objective function. This is the objective. This is the goal that we want to achieve, and that is we have defined the best model as the model that minimizes the total squares of the residuals, okay? And so the residuals, the difference between the actual and the predicted value. So the line predicts this spot, okay? and the actual values up here, and then we have this difference, right? That's the residual. And least squares says we want the smallest residuals, okay? We want the smallest residuals, the squares of residuals. We want the smallest total squares of residuals, okay? And so this thing represents a thing that we want to minimize. This may also be called a loss function or a cost function. We have like a bunch of things for the same thing. You have an objective function, or we might call it a loss function or a cost function. Yeah, question?
The loss function, what is being lost?
The thing that's being lost is the difference between the actual and the predicted, right? It's how much difference there is between what you want to get. Like ideally, we can predict everything perfectly, and
I get what RSS is doing, but the name loss function. So
yeah, you basically it's just things that are bad, right? We want to minimize our costs, we want to minimize our losses, okay? We could have just called this the badness function, right? And we want to minimize that, right? Except that, like, somebody can just say, we're going to call this the badness function and let's minimize that, right? So it's just synonyms for bad things. So losses and costs are just generally the things that we want to minimize, all right? All right. So anyway, we call this class optimization, and many machine learning models count as optimization problems. So linear regression, we're trying to minimize that RSS, okay? And in this case, we're other things we're going to try to maximize an objective function. We'll call that later, okay? And so linear regression, I'm hoping, is super familiar to everybody, and we are going to just apply some machine learning concepts to this and start here, okay? So if it feels like review, it's by design because I want to frame everything in a context that you're familiar with. Okay. The textbook notation, they don't do this. They don't write y and y hat. They write tn. This is the, I don't know, the truth, I guess. Okay, this is the true value of the observation. And then this is what we predict by our function, okay? The function is a function of our inputs x along with the parameters w0 and w1, which represent the slope, the intercept and the slope, okay? So the function is, the value we plug in for x along with the parameters of the intercept and the slope, and that's our prediction. And so anyway, these two things are equivalent. We've just called y's the t sub n, and then y hat is the result of our function, okay? And this function is an arbitrary function, although in our case, because we're using a linear model, it's a straight line function. But this form can generalize to anything where the function is just something else, right? And then our book likes to use the mean squared error, so it just takes the mean 1 over n of the RSS, basically. Okay. And another thing you'll encounter is the root mean squared error, and you just take the square root of it. What did I say? The root, yeah, mean squared error, yeah, the square root of that. Okay, not a big deal. Okay, so anyway, I'm going to just kind of blitz through this. I think you had to already do this in 100B, right? You had to derive RSS using calculus in 100B? No? No?
if we didn't know what we're doing.
Okay, So nobody had to figure out what the slope and intercept were using calculus in 101A?
No, using calculus was in 100C.
100C. Okay, then in 100C, and maybe some of you haven't taken 100C. Okay, well, this is covered in another class, either 100B or 100C or something, right, where you're going to derive this in calculus. So I'm going to just fly through this, okay? All right, so basically, our loss function, this is the thing that we want to minimize, okay? And basically, we want to find the values of w0 and w1 that is going to minimize this loss function, okay? Sorry, this is running over here and hard to read, okay? So basically, I just expand this out, and we get this, right? Okay, so this, just trust me on this. And then how do you minimize a function in calculus? You take the derivative, you set it equal to 0, and you solve, right? And what if it's a function of two variables? In this case, we've got w0 and w1. What do? You do partial derivatives, right? Partial with respect to w0, partial with respect to w1. You're going to get a system of equations and solve for that. Okay, so that's what we did. Here's the partial of the loss function with respect to the slope. Here's the partial of the loss function with respect to the intercept. We're going to set them equal to 0 and solve. I'm skipping all of that and saying, trust me, it works. If you want the details, you can read it in the textbook in section 114. And you solve, okay? And you're going to get w0 hat and w1 hat, and it's going to be, you know, whatever the things that you guys get, right? R times sy over sx and things like that, okay? I have to now talk about linear algebra, okay? So we deal with a bunch of observations, and so we're going to always have a sum of x and things like that, and a sum of tn and things like that. And it can be annoying to have to deal with these sums, okay? And so if we turn everything into matrix form, when you do kind of matrix operations and you do like a matrix times a matrix, that summation is part of your matrix multiplication operation, okay? And so it's often very helpful to reframe things in matrix notation using linear algebra, okay? And I don't know when was the last time you took, what is it, 33A for your linear algebra and stuff. It's probably a good idea to review your linear algebra. There is a playlist on YouTube, and this is like the best set of videos, I want to say almost ever, but at least on linear algebra. It's like, it's amazing. I don't know how to praise how beautiful these videos are, okay? So please watch these videos, okay? And this person on YouTube, 3 Blue, 1 Brown, has a series of videos on linear algebra. Each one's maybe like 10 minutes or less, something around there. Okay, this one's 12 minutes. But you can watch this in a couple of hours, okay? It's a better use of your time than rewatching Avengers, okay? Which was excellent, by the way, and so that's how good this set of videos is. Okay, so anyway, make sure you do watch those things with the thing, and so here I'll go over it in linear algebra. Okay, so rather than having to write out our intercept and our slope this way, okay, we can say we've got a vector or a matrix W, a 2x1 matrix W, and we can say each observation in X, so this is the nth observation in X, is going to be 1 in Xn, okay? And we can say the prediction that we make using linear algebra is just W transpose Xn, okay? And so this is for one observation, for xn. If we want to do it for the entire set of observations, okay, we can do this, okay? So if we can say big matrix X has each observation going like this, 1 and x1 and 1 and x2 and things like that. We have a column of 1s and a column of x's. Then we can do x times w, okay? Keep in mind w looks like this, all right? So you've got x times w, and this will be equal to basically a vertical vector of these things, okay? And so our loss function will be the difference between the actuals, the t minus xw transpose times t minus xw, right? So here I just kind of expand this out. So x times w will look like this. X times w, when you multiply that out, will look like this. And so this is what we have. Anytime you're doing linear algebra, it's very easy to get things wrong if you're not careful, all right? So one thing I recommend is putting little, I don't know what you call these things. They're not subscripts, but something underneath so you know the dimensions, right? So you do say X is an n by 2 matrix and W is a 2 by 1. And when you do matrix multiplication, you know that the inner dimensions need to match, right? If you're going to do n by 2, the next thing has to be 2 by something, all right? And so the result will be n by 1. And so this is what we have. X times W is n by 1, and that's what we've got here. Okay, so if you do that, that will help you avoid a lot of common mistakes in linear algebra. Okay. Side note, if you wanted to do this in R, you can create a vector of 1s and then do column bind, C bind the 1s and the X values, okay? And then, and here I've got my matrix W, okay? And so we got 28 by 2 and 2 by 1, and I can multiply these together, right? So X times W is going to be 28 times 1. And if I do the other thing, W times X, okay, you get non-conformable arguments. So anytime you get this error in R, non-conformable arguments, it means you have a dimension mismatch. So here what I'm doing is I'm doing 2 by 1 times 28 by 2. That's not going to work, okay? Okay, so going back, we have xw is this. These are our predictions. We've got n of them, and we do t minus xw, which is this, okay? N by 1, and we're subtracting off n by 1, so the result is n by 1, okay? And then the squared residuals, which is this, can be just written as t minus xw transpose times t minus xw. And I've kind of written this out, and I'm going over this kind of quickly, but basically, this is what we want. The sum of squared errors, t minus our prediction squared, and that can be written this way, okay? And we can see that, indeed, when I do this, this is going to be this value times the first row, the second value times the second row, and the nth value times the nth row. And each of these things will be squared, and the matrix operation takes care of the summation, okay? So we can avoid having to write out the summation by using matrix operations. And this is very handy for us, okay? Is that good? Okay. And so here I can expand this out, and I'll let you guys just follow this on your own time. But you can expand out the matrix multiplication and get this. Yeah. Question? No. What?
Yeah, yes. I got the first part. It's not clear how you got t minus xw, much less what xw actually is.
I don't know what you, sorry?
We've only defined w0 and w1. Which one is w in that case? Like, what is w with xw?
W is the matrix that represents w0 and w1. A matrix contains multiple values. Yeah. So w0 and w1 are contained in w here. Okay.
How did we get?
I've got a lot to cover here. Okay. So if you got questions, I'm happy to answer them in office hours and things like that. I've just got a lot of slides to cover. I don't mean to dismiss your questions, but that's I've got a lot to cover here. Okay, so I'll take a moment, and so this is what we have. I will let you review this and make sure that this goes. But basically, we can expand this t minus xw transpose, applying the rules of how transpose things work, and you're gonna have to you have to review your linear algebra stuff to see, like, when you distribute a transpose, it flips things around and does w transpose, x transpose, and stuff like that. And then here I've written the dimensions underneath each thing, so you can make sure that everything does indeed. And when you do this, everything lines up to be 1 by 1, and you get a scalar, okay? Which is perfect for what we want, because we want a loss function. Yeah?
Yeah, going to pause and scribble. Will we get these slides on CCL?
Of course. Yeah, it's not just a one-time only thing. Yeah, so you don't have to madly copy everything down, all right? Okay, so anyway, there's all of this stuff. And so now, just like before, we want to find the W the W0 and the W1 that will minimize our thing. And now W is represented as a matrix, okay? The matrix now contains all the parameters, W0, W1, or however many other W's you might have. And we can use matrix calculus to optimize this. So now we have a function of the loss function, and we want to minimize this with respect to W, right? We want to find the parameters that will do this, right? So we're going to take the derivative with respect to W, set it equal to 0, and solve for W, okay? And so we're going to do this. This is just what I've said. We're going to set it equal to 0 and do this, okay? And so have you guys done matrix calculus? Maybe taking derivatives with respect to vectors? Maybe? Okay, sometimes it gets messy, and so this is just a very quick review, okay? So with a derivative, you've got a function that goes from one real number to one real number, right? You've got a mapping that maps basically the x reals to the y reals and things like that. And we define the derivative as what happens when you add on a little thing called h, right? And we say, what if I add h to x and I take the difference it makes on the function, right? What is f of x plus h minus f of x, right? And then we say, okay, so how much did the function change in this much when I added this much to the x, right? And when we take that limit for h equal to 0, that's when we get the derivative. All right, this should be review, and this should all feel good, okay? Another way we can do this is we can say that if we solve f prime, the derivative, it's also going to satisfy this equation here, okay? Where if we do this, and minus this thing, it satisfies this, okay? And so similarly, when we do this in matrix notation, we have a function of a vector, okay? In this case, I've got a function of W, which represents the values W0 and W1. And so that's taking something that exists in n-dimensional space, and it's mapping it to one real number, okay? So we've got our loss function says, give me the slope and give me the intercept, and I will tell you the total squared error or the mean squared error, okay? The mean squared error is a single number, so that's a real number, and it's a single one-dimensional real number, so it's in R, just one-dimensional R space, whereas it was a function of two values. It was a function of the intercept and the function of the slope, right? W0 and W1 in n space, so that's two-dimensional space, and it's mapping it from two-dimensional space to this, okay? All right, so just avoiding a little bit of stuff, everything basically becomes vectors and matrices, and similarly, so just like this thing over here, we get something similar, okay? And this thing, this is called nabla, okay? Nabla of f, this is basically the derivative of f, but it's a multi-dimensional derivative, okay? And when we do this, it will satisfy this thing, okay? Basically, one thing that I always find helpful is that the gradient, okay, which is basically the multi-dimensional generalization of a derivative, okay? So the gradient or the derivative with respect to a vector has the same dimensions as the vector, okay? So if you're taking the gradient of a scalar function, which is what we have, we've got the mean squared error, which is one single value. If you take the gradient of a scalar function with respect to a vector W, okay, so W right now is two dimensions, W0, W1, okay, but it can generalize to n dimensions, okay? When you take it with respect to an n-dimensional vector, the resulting gradient is also an n-dimensional vector. All right. All right, so if I take, I've got a scalar function right now. It takes two values in, the slope and the intercept, and it reports back the total squared error or the mean squared error, okay? And if I take the derivative or the gradient of the mean squared error with respect to my inputs w, okay, then I'm going to get a two-dimensional value back, okay? So, and they end up just being the partial with respect to each element in w, okay? So in our case, I've got w is w0, the intercept, and w1, the slope, and it's going to be just the partial with respect to the intercept and the partial with respect to the slope, okay? So, like the derivative, the gradient represents the slope of the tangent of the graph of the function, okay? And in this case, because it's a function in two-dimensional space, okay, the function represents a surface, and the gradient is basically a tangential vector pointing in the direction of the steepest slope, okay? So you can imagine being on a hill, right? So imagine you're on a hillside, and the gradient of your location on that hillside is going to be the direction that is the steepest direction at your location, okay? So because on your hillside, you can choose to kind of, I don't know, so just imagine, being on a hill, okay? You can choose to walk like sideways, and maybe you won't be gaining any elevation, and that will be like the easiest path, right? But if you wanted to get to the top, you're going to have to kind of go in the steepest way. And so the gradient at that location is the direction that points in the steepest ascent, okay? So that's kind of how we can visualize this, right? So on a regular old in your univariate calculus class, you learn that the derivative is like the slope of the tangent line, and in our case, it's going to be the direction of the vector that points in the steepest ascent. Here are some useful gradient derivative relationships, okay? So if you have w transpose x, okay, and so this again is assuming that all of these things are scalar values, right? So if we got w is 2 by 1, so this is going to be like 1 by 2 and 2 by something. And you take this with respect to w, you get x. Here's x transpose w. Again, if this is a scalar and you take it with respect to w, you're going to get x. There's w transpose w. You take the gradient of this with respect to w, and you get 2w. Okay, so you can kind of think of this as like w squared almost. Okay, and so in the way that x squared, the derivative of that is 2x. You get this, okay? And here we've got w transpose c being a matrix, square matrix, w, okay? And the gradient of that is going to be 2c times w, okay? All right, so we left off, earlier I did all of this stuff to kind of expand this thing out, and we got to this location here, okay? And what we're going to do is we're going to take the gradient of L, the loss function, with respect to w, okay? And this is what we get, okay? So if I take the gradient of this with respect to w, this is t transpose t, w is not even in there, okay? So it's like taking the gradient of a constant, as at least with respect to w, it's going to zero out, okay? And again, this is a 2 by 1 zero vector, because if it's a scalar value here, the gradient has to have the same dimensions as the vector with which you're taking it respect to something. Okay, so anyway, so we get this. I'm just applying this, right? Taking the rules here, and so we get 2 by n by 1, and we do this, and we get the gradient of this, okay? And this reduces here. Yeah, another question.
What does it actually mean to take the gradient with respect to a vector?
What does it mean to take the gradient with respect to a vector? Yeah, so what does it mean to take the gradient of a function with respect to x? It just means how much does the function change when I change x by a minuscule amount, right? So what is the slope at that location, okay? And so now a vector is just a multi-dimensional version of whatever it is that we're talking about, okay? So now we've got, so before we had a one-dimensional function, you put one x in and you get one y out, okay? Now we've got a multi-dimensional thing. So think of, you got a W0 and a W1. How much is it changing with respect to our inputs? How much does it change with respect to W0? How much does it change with respect to W1? Yeah, keep going.
Sorry, I should have been more specific. What does it mean in the mechanical sense?
I don't know what you mean by that.
We're talking about like this, that, the other, but it's like, what does it mean in the mechanical sense? Like, how is operation even performed? Like, I can get into the more philosophical stuff once I understood that, but
I'm sorry, I still don't understand your question. By mechanical, I'm just showing you what this is in terms of,
yeah, so as we can see, I suppose the first term turns to 0, WT disappeared.
uh-huh.
So applying the derivative to WT, what actually happened? Is it like 1 plus 0 and then 1 plus 0 or 0 plus 1? Is that it? Like,
I am so sorry.
it's fine. I'll ask that. That's it.
Okay, please do. Yeah, this is kind of our, we're using this, W's with respect to x. I mean, the function outputs a scalar, and you're taking it with respect to some vector, and you're getting back another vector there. Okay, so I'm just applying these kind of identities, which we can derive, but we're not going to bother doing that here. Okay, and so anyway, I take the derivative of the loss function with respect to w, and I get this at this point. Okay. And continuing on here, so now that I've taken this with respect to w, we're going to set it equal to 0 and solve for w. Okay, so you take the derivative and you're going to set it equal to 0 and solve for that value, and that's where we leave. Go on the next slide. Okay, so I'm taking that. The gradient looks like this. I set it equal to 0, and I'm going to solve for w. So at this point, I can just add this to the other side. And then, and what do I do here? In linear algebra, you are not allowed to do division, okay? Division doesn't exist in linear algebra. All you can do is multiply by inverses, okay? And so to cancel out the x transpose x on this side, we multiply it by x transpose x inverse, and we multiply that over here, okay? And we get this, okay? And I don't know if this looks familiar. Okay, this is the OLS result, okay, for in matrix notation, where you have x transpose x inverse, x transpose t, or in a lot of cases you might have seen it as x transpose y, okay? And so this might be a familiar appearance in matrix notation regarding the solution to ordinary least squares, okay? So if you're nodding your head, then you have seen this derivation in matrix form. Okay, so not a big deal here, right? Okay, so anyway, this is what we've got. Here's a quick example. I'm just doing 1, 2, 3, 4, 1, 3, 2, 4. This is a set of 4 points, and if we want to find the best fitting line, okay, we can throw this into R, okay, and we get this, and we do x transpose x, and we get this. We can take the inverse, and we can do x transpose x times x transpose, okay, and we get this, right? So x transpose x inverse is 2 by 2, x transpose x times x transpose is 2 by 4, and we multiply that by t, which is going to be 4 by 1, and we get this. The intercept is 0.5, and the slope is 0.8, okay? So these are coefficient estimates, 0.5 for the intercept, 0.8 for the slope. If we do call R and we just say find the linear model that fits t according to x, we get 0.5 and 0.8. So our answers match, okay? Maybe this is not a surprise, but it does show that we can do our matrix operations and get the same thing that the linear model in R does, okay? The linear model in R actually does something different. It's not doing these matrix inverses, which is actually computationally expensive. Don't worry about that. Okay, so to get predictions, all we have to do is just plug in x and multiply it by our predicted values, which are w hat, right? So w hat is currently this matrix where it says the intercept is 0.5 and the slope is 0.8. We multiply x times our w hat and we get these values back. And if I plot that and I connect them with a straight line, this is our best fitting line here. Okay.
What was x again? Sorry.
In our case, x is our input matrix of back here where I've got x is 1, 2, 3, 4, and a column of ones, right? So x is currently
A matrix.
a matrix, yeah, a matrix. Yeah. All right, is that good? Okay, and we can do the same thing. We just expand it for our bigger data set. Here's the Olympic data starting in 1896 and I think 2008, looking at the 100-meter race times, and they get faster and faster. And the linear model, if we did LM with R, it says the intercept is 36.309 and the slope is that we get negative 0.013, so we're improving by 0.013 seconds every single year, okay? 1/100th of a second every year, according to this linear model. To do it with matrix notation, we just take our x inputs and we bind a column of ones to them, okay?
Why
Yeah.
do that?
Why do I do that? Because in order to get the dimensions to line up, right? So our w's are w0 and w1, and our x has to then have two columns in order to multiply properly, okay? And so if I just have a column of x, it's not going to work. I have to, and if we think about what this, if we just think of everything as being just like the column over here times the element over here, having a column of ones makes sense there, okay? Anyway, so I do this, and then I do x transpose x, x transpose t, in this case the times, and we get the same values, 36.309 and negative 0.0132. Okay, so we get the same values there. Okay, and again, we can do x times our w hat, and we get our predicted values, and we get this as a straight line here. Okay, so so that's that, and this is just to kind of show that the whole reason why we went through all of this painful stuff, or maybe it wasn't even that painful, is to show that linear regression at its heart is an optimization problem. Okay, at its heart we have a function which is the RSS, the sum of squares residuals, or if you divide that by n, then it's the mean squared error. Okay, and we just want to minimize that. Okay, and just like using all of our concepts from regular old calculus, where you take the derivative and you set it equal to 0 and then you solve, that worked here. Okay, and I showed it to you kind of using the partial derivatives, although I didn't really show it to you. And then we did a little bit of stuff with the matrix calculus, or vector calculus, to show that we can take the derivative, or in this case the gradient, set it equal to 0 and solve. Okay, this was a lot to take in. Okay, and please go through and review some of these slides on your own time to kind of just make sure you understand each of these linear algebra steps. And I've kind of glossed over them quickly in the interest of time, just because I'm trying to crunch 10 weeks of stuff, and I'm going to have to excise some stuff, which breaks my heart a little bit. But we're going to work through it, okay? And also, it's also covered in the textbook in great detail as well, and so you can kind of follow those along, and perhaps the textbook answers some of your questions, answering what exactly is happening mechanically regarding these things, and so that's what we've got going on. Okay, the beauty of using vector notation and matrix notation is that we can then scale up our equations and stuff, and it doesn't cost us anything, at least in terms of hurting our brains. Okay, so for example, if we continue on with our Olympic data, what if we said, well, you know what? The linear trend, that works now, but certainly that can't go on forever, because that means by the year 2500, we're going to finish the 100-meter race time in negative amounts of time, right? So obviously that trend can't hold forever, right? And so we might say, well, we've got to introduce something that's nonlinear, okay? And someone will say, well, maybe it makes sense to just throw in a quadratic term in there, okay? So we can just say, all right, let's take our X matrix, which is currently ones, and the X values, and let's throw in a squared thing, okay? And you know, for the Olympic data, our X's are the years, and so it's like 1900 and the year 2000. The year 2000 squared is like 4 million, which are huge numbers, but it's fine, okay? You know, mathematically it doesn't hurt us, okay? So here we go. We can just take this, and then I can just take X and I can square them, and I got, you know, 1900 squared is whatever this number is, 3,610,000 or something like that, okay? So now I've got our X matrix, which has n rows and 3 columns, okay? Which means that my W vector now has to have 3 elements, okay? It's gonna have an intercept and a term for the linear component and a term for the quadratic component, okay? And so it's gonna become W0 plus W1xn and W2xn squared, all right? So we've got that, okay? However, if we just say W is W0, W1, and W2, okay, then the result is just W transpose xn, okay? So this part is still exactly the same as what we had before, okay? And so, so if we wanted to solve this using regular old calculus, one dimension, one variable at a time, we would have to find the partial with respect to W0, the partial with respect to W1, the partial with respect to W2, and then solve a system of 3 equations, okay? Which is not going to be fun. But by using matrix and vector notation, I can leave it as the vector W and the vector X sub n, okay? Or I can use the matrix X and the vector W, and we still get this, okay? So here I've got X times W, you know, expanded to 3 columns, and W is a vector of 3, and we get this, okay? So here this is, what is the dimension of this thing? N by 1, okay? So our predictions are still n by 1, which is exactly what we want, okay? The loss function is exactly what it was before, okay? T minus xw transpose times T minus xw, okay? And so adding another column to X and adding another term to W doesn't change the form of the loss function. So all the work that I did in vector calculus and all of that will be exactly the same. Nothing has changed, and so when I want to solve L with respect to W, okay, find the gradient of L with respect to W, everything remains the same. I don't have to solve a system of 3 equations and find 3 partial derivatives. So this is the advantage of working in vector notation, okay? And I know, like, the leap to go from univariate calculus to vector notation calculus, that it's uncomfortable and it's not fun. But you gain benefits here. Now that we're here, I can keep adding more and more terms, and I don't have to redo all of my partial derivatives or anything like that. Okay, and so to estimate the parameters, we're going to end up getting the same thing, right? X transpose X inverse X transpose T, okay? We don't have to go through all of those steps again. All right, so far so good? Okay, if we try to do this, however, all right, so back here, this is my X matrix, except there's, I think, 28 rows or something, 28 Olympiads or something. If I try to run this, and I say, all right, R, do X transpose X, solve X transpose time, I get an error. What happened? I got system is computationally singular, blah, 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 something. Okay, what do you think is going on? Yeah.
Is the solve function asking for the inverse?
Yeah, sorry, that wasn't made clear. Yeah, when you do, if you want the inverse of a matrix in R, the command is solve. Yeah, so X transpose X is X transpose X, and then solve of X transpose X is the X transpose X inverse, okay? But when I try to do this, it gives me an error. What's going on?
It's not really a square anymore, right? So that could be it.
No, it is a square. If I do this, okay, X transpose X, and I multiply this, right? This is 28 by 3, and if I transpose that, it's going to be 3 by 28 times 28 by 3. I'm going to get a 3 by 3 matrix. I still have a square matrix. The issue isn't that I have a square matrix. What happens is if I do X transpose X, look at the number I get, okay? So this is fine, 28, 54,726, that's fine. But because I have that column of X squareds, right? And remember, like the year 2000 squared is 4 million, okay? And then I'm doing X transpose X, so I'm kind of multiplying it by itself. So I'm doing 4 million times 4 million, which is going to be 16 to this, whatever, right? A huge number, 16 times 10 to the 12th. And then I'm summing this up. So I've got a bunch of things on the order of 10 to the 12th or something, 16 times 10 to the 12th, 1.6 times 10 to the 13th. And I'm summing this up across 28 numbers. I'm getting a number on the order of 10 to the 14th, which is, what is that? Million, billion, trillion, quadrillion, something, I don't know. I can't even count that high, okay? So my daughter, who's 5, asked me, how high can you count? I said, I can count really high, but I don't know what comes after. Is it decillion? I don't know. Quadrillion, heptillion, quintillion, sextillion, septillion, octillion, nonillion. All right, I got my roots down. All right, then what's after nonillion? Yeah, decillion, who knows? So that's the limits of my counting, okay? I don't think I would live to count that high, but I say I can count high, but I don't think I can count to this number, right? Because I don't even know how to say it. So anyway, the problem is this, is that we are dealing in computational numbers, not real numbers, right? So real numbers, this is not a problem to take the inverse of this. But if I try to take the inverse of this computationally, I run into some underflow errors, right? So in R or on a computer, you cannot represent really small numbers without running into some computational difficulties, because we don't actually have all the real numbers. We only have certain finite set of numbers, okay? So we run into the limits of floating point computation, which is something that we often don't think about. We often just think our computer's working fine. And so this is an issue that we encounter. And so we just have to do some stuff. So what I propose to do is I just multiply everything by, or I divide everything by 10,000, or multiply everything by 0.0001. And so that scales things down. So instead of 4 million, I have numbers like 365.57, okay? So I do this, and then I can do X transpose X inverse, okay? I can scale everything and then take the inverse, and now I've avoided the issue. Okay, so the issue was I just had too big of a number, all right? And the computer couldn't handle it, right? So just like back in 6th grade and you had a calculator and you tried to do like a really big number and it gives you an error. That happened, right? Like,
how does the LM function do it then?
huh?
How does the LM function do it if you have the square?
How does the LM function do it? Oh, that's a good question. I actually don't know the underworkings of LM. They don't do matrix inverses, because matrix inverses is actually slow on the computer, and they have other algorithms to solve this. And to be honest, I don't know. I never looked at what the inner workings of LM does. So it does something and it's trustworthy. But I don't know really what it's doing, okay? But anyway, if we wanted to insist on using this X transpose X inverse business, this is how we could go about doing it to avoid some of these issues. All I'm doing is just scaling this number down by a bit, okay? And then it tells me here's my intercept and the W1 coefficient and the W2 coefficient estimates, okay? So this is my W hat. So now I have 3 terms here. And again, if I did LM, I get the same coefficients using the scaled matrix. And we can ask for our predictions. And when we fit the predictions here and we graph the line, we get a quadratic looking curve, okay? And this seems to, that makes sense. Like, I don't know how much faster the people will get, okay? But it's probably going to level off. Now, at that point, the quadratic model fails because it's going to start going up. And it means like by the year 2050, they're going to take 3 minutes to run the 100 meters, which is also not true, right? So so as we say, all models are wrong, but some are useful. And this is useful for now, but probably is not correct because it's not going to work in the future. Okay, there's a function called poly, and it does stuff. It basically takes a linear component and it does, and it can do like a quadratic and a polynomial component, and it does something interesting. And I don't know the actual inner details of poly, but it is a useful function to have. So if you want to fit a polynomial thing, if you want to know if there's a linear trend or a quadratic or a cubic or whatever, tetra something, is that what we would say next? Fourth order polynomial relationship between x and our output y, I would recommend using poly rather than taking your x's and doing x squared and x cubed and x to the fourth, okay? The reason for that is that if you do x and x squared and x cubed and x fourth, all of those values become highly correlated, right? Like as x squared gets bigger, x cubed also gets bigger, and x to the fourth also gets bigger, at least on the positive side. And what happens when your values exhibit high collinearity? You learned this in 101A, right? This sounds familiar? So what happens when your X matrix or your X variables have high collinearity, or the problem of multicollinearity? What happens there? Yeah, the variance of your estimates is really high, and it's very sensitive to just little fluctuations. And so if two people have very similar data sets but slightly different, one might say like this term is very important, and then the other person might find that this term is not important and the other term is important, right? So that's a problem when you have high collinearity. Just small things can lead to large variances in the coefficient of estimates. And so what poly does is it decorrelates these terms, at least on the range of x, okay? I don't even know if this makes sense. But basically, you will find a relationship. These coefficients, the problem with poly, however, is that the coefficients here lose a lot of meaning, okay? You lose a lot of interpretability, whereas before it was like, if I increase x squared by this much, then my y changes by this much. Now we lose a lot of the interpretation because it's no longer x squared, it's like a transform of x. However, it will tell you whether there is a statistically significant relationship to a squared relationship or cubic relationship or something. So it will help you identify if there's a significant higher order polynomial relationship, but the interpretation of each coefficient is lost. That's the trade-off, okay? But it helps combat some of these things, okay? So you still get the fitted polynomials, and so here I can fit a bunch of these things third order polynomial, fourth order, fifth, and sixth order polynomials, okay? And I can fill all these things, and this is just a pretty slide of just either straight line or quadratic or something like that, okay? And then what you would then do is you would ask for like the summary of this, and you can see, you know, how many stars there are to decide whether these are significant or not. Yeah, question?
Well, that really gets to the heart of like, what is up with x squared anyways? Like, originally you said, people said, let's just throw it in, like, all right, it sounds cool. But now it seems like it actually matters. What's the deal?
Yeah, well, so the issue is always, should we add another term? Like, does it help to add this extra term in explaining something, right? And so, because sometimes there does exist a relationship between the squared or the cubic thing. So for example, like the simplest example is, how much paint do I need to paint a square room, right? And all you have is the length of one wall, okay? The amount of paint you need has a squared relationship to the length of the room, okay? We're assuming we're gonna paint the floor, okay? So there's a squared relationship there, right? And there's other things in life like gravity. The strength of gravity has a squared relationship to the distance, right? And things. So the squared relationship does exist, and in other cases, a cubic relationship does exist. And so in statistics, when we model something, we don't really know what's happening. Like we don't, like if we're going to paint a square room, that's easy. We can say, okay, I'm going to need square amount of paint. But in statistics, we are dealing in a situation where we have data and we have inputs and we have outputs, and we're not quite sure the relationship. We're not sure if there's a squared relationship. We're not sure if there's a cubic relationship. And so we have to kind of try these out using trial and error. We say, well, what happens if I fit a squared relationship? Does that seem to do a better job? What happens if I do a cubic relationship? Does that do a better job? Yeah.
So in that case, the relationship is in W1 and W2.
What? So W1 is the coefficient for the linear component, and W2 is the coefficient for the quadratic component.
Okay, but like obviously x and x have correlation, so it doesn't make sense to say x is square correlation with x. So I'm saying W1.
So we are looking, we don't care if x is related to x squared. We are curious if y, or the t, the output, is related to x squared, or if the output is related to x, right? So if I'm going to paint the floor of the room, the length of the room only influences the amount of paint in terms of the squared relationship. The floor depends on the length of the room squared. Now, if I also needed to paint the perimeter, okay, then the perimeter has a linear relationship to the length of the room, right? So if I'm also going to paint the perimeter, then I need to do 4 times the length of the room. And if I need to paint the floor, I need to do the length of the room squared, okay? And so in that case, if you're going to paint the perimeter and the floor, then the amount of paint you need will have a linear aspect and a quadratic aspect, right? If you're only going to paint the perimeter, there's only a linear relationship to the length of the room. You just take 4 and you multiply it by the length of the room, and I guess the width of the paint, you multiply that by some constant as well. If you're going to paint the floor, you got to add a thing, right? And if you're going to fill the room with, I don't know, if you're going to fill the volume, there's a cubic relationship, okay? But the thing in statistics is we don't necessarily know exactly what's happening. We don't know what's happening. We can only infer these relationships from the data. We say, okay, this is what I'm seeing, right? It's like in some weird world, you're getting back paint receipts. You know, how much money did you spend on paint? And then you get one dimension of the room, okay? And then you're trying to figure out, okay, Is this person painting the walls? Is this person painting the floor? What is this person doing? And we're trying to infer that relationship by looking at the data. And so if the data comes back and says, oh, there's a squared relationship, then we can say, oh, okay, there's some kind of quadratic relationship going on. Maybe, maybe not. Yeah.
Well, I think I get it, to be honest, but the final question, you said scaling induces correlation. Wouldn't it already be correlation? Like, how can x and x squared not be correlated? Like,
Yeah, x and x squared are correlated, okay? But if you use the function poly, it decorrelates.
no, I understood that, but you said scaling induces correlation.
I don't know if I said that. Scaling allows, the scaling thing is to avoid the computational difficulties of having these massively large numbers that break the floating point system of a computational system, okay?
Yeah, wait, go back to that. Instead of right there, 2 slides back. While scaling down big numbers works, our values can become very highly correlated.
Yeah, that's for polynomials of high degree. Our values can become very highly correlated. So that's the issue of x and x squared and x cubed being all highly correlated. But it's not the issue of scaling, okay? It's the issue of doing x and x squared and x cubed and x to the fourth. Those all become correlated. And scaling will help with our thing here, but doesn't take away the problem of the correlations, okay? And so poly decorrelates these things, and we can find these relationships there. Okay? Oh, we're doing great. I was afraid we were going to run out of time to finish this, so I'm going to jump into my other prepared slides here. Okay? And so anyway, when we do LM, and you're trying to decide, do I do a quadratic model or a cubic model or something like that, what you end up using is what? You do something like summary, and you would look at these stars, and you'd say, okay, well, there's stars here, so they're significant, right? You look at this thing, and what do we say? We say if it's smaller than 0.05, we keep it, and if it's bigger than 0.05, we drop it. This is kind of how, I don't know. and there's something probably uncomfortable about doing something like that, right? Some things feels like, I'm not sure, right? So here's the 6th order polynomial. We look at this and we go, okay, poly, the 4th one and the 5th one and the 6th one, those are not significant, so probably I won't keep those, okay? And maybe that's okay. In 101A, you probably learned about like AIC and BIC and forward subset and things like that, right? And those are all fine, okay? What we also have is we've got another way to decide on which model to select, okay? So let me pull this up. Okay. And so let me introduce cross-validation. All right. And some of you guys are probably already familiar with cross-validation. Okay. And cross-validation is the idea of having the data, using the data to try to decide to kind of verify how many predictors we need, okay? All right, and so just going back, the classical approach as far as choosing which model to use, do I use the squared model, do I use the cubic model, do I use the 4th order polynomial or something, that requires knowledge about the variables in a lot of cases, right? So if we're talking about something, we just ask, does it make sense for there to be a squared or a cubic relationship, right? And if it's something, if we're talking about something like painting the room, we say, oh yeah, that makes sense to use a squared relationship, right? And if we use something, doing something about gas mileage and the effect of, the weight of the car and its effect on gas mileage, like we're not quite sure, but from physics, we're like, Yeah, I guess it makes sense that heavier vehicles, like, is going to consume more gas and something. It might make sense to have a squared relationship somewhere in there, right? So we try to think to our knowledge of physics in the world or something, and we just say, well, maybe this does make sense, right? But sometimes it doesn't. Like, our brains can't fathom this, right? Like, does the race time have a sixth order polynomial relationship to the year in which the race took place? And we're like, I don't know, what is a sixth order polynomial, and what does that even mean, right? Like, I don't know what in the world, if there's a real world thing that has a sixth order polynomial relationship. I'm sure there's something out there, but I don't know, right? And my brain has a hard time thinking more than cubic relationships. But who knows? Maybe there's something. And these things are hard to reason about. And so what machine learning kind of does is that we take away this skillful or maybe arbitrary thinking, and we replace it with a validation strategy, okay? So now we just say, well, I don't know. Squared, cubic, fourth order, I don't know what's good. Let's just try it out. Let's see how our predictions go. If our predictions are good, it's got to be good, right? And that's kind of that's the approach that we take. Is that a good approach? I don't know, okay? But it's very common, okay? And if you do machine learning in Python, that's like not the only approach, but that's like the primary tool that we use for deciding which model to keep, okay? So I teach a class on Python, and we do this, okay? And that's how it does the validation approach, okay? And so cross-validation, what this will do is it will split our data, the data that we have, it splits it into a training set and a validation set, okay? And we use the training set, okay? We don't use any of the validation data. We use only the training set to fit the model. So we say, looking only at this subset of the data, figure out the best coefficients, figure out the best intercept, figure out the best slope, figure out the best whatever coefficients you need for the model, okay? And so we fit it on this segment of the data, and then we say, okay, this is the best model that I have for this set of data. Let's see how well does it predict the data that I didn't use, okay? So, you know, we have the validation set, and we say, okay, does this do a good job of predicting these data points, okay? And then, and we can do this for, you know, a linear model. We can do this for a quadratic model, a third order, fourth order, fifth order polynomial. We can do this for different models, and based on how well or not well it predicts those points, we can decide which is the best performing model, okay? So kind of the first thing that we might encounter is leave one out cross-validation, okay? And what this says is it takes the entire data set, okay, and it takes out one observation, and it says this is going to be the validation observation, okay? And so, maybe our current data set, we've got 28 points. It's going to fit a model on 27 points, okay? It uses just 27 of those points to fit the model, and then it leaves out this one observation. It says, okay, how well did you predict this one observation, okay? And then it does it for every single data point. It does the same thing for every single data point. So it's going to, if you got 28 observations in your data, it's going to fit 28 different models, okay? The first one will be to predict, you know, point 28, okay? Uses observations 1 through 27, predict point 28. Okay, and the next one will be observations 1 through 26 and observation 28, and it'll predict point 27 or something like that, okay? And it'll go through And each observation will have a turn at being the validation observation, and all the other data points will get used for the training. Okay, so for example, here's kind of just my toy data set. So I've got 4 data points. The x's are 1, 2, 3, 4, and the t, our outputs are 1, 3, 2, and 4. Okay, so this is, I think I've got this data set somewhere back here. Okay, so this is what we've got. All right, so this is our observations 1, 2, 3, 4, and our outputs are 1, 3, 2, 4. Okay, so not a perfect line. And the linear model in this case looks something like this. When we fit all 4 data points, it's going to look like this. Okay, and so what we're going to do is we're going to just say, let's use observations, the first 3 observations. 1, 2, 3 will be my training, and then the 4th point, the last point, will be my validation point. Okay, and so in R, I'm going to say the indexes that I'm going to use for my training data will be X subset the index of 1, 2, 3, and the training on the T will be, I subset that, and the validation, I just do everything but the training indices, right? So minus the index and minus this index, okay. And then we do the training data, and then I say, all right, fit the model where you train T, fit T based on X using the training data. Okay, and so this is the linear fit on all the data points. And if you only use points 1, 2, 3, this is the linear fit. Okay, so when you use only these 3 points, this is the best fitting linear model. Okay, so when you have all of them, this is what it looks like. When you only have 3 data points, this is what it looks like. Okay, and so the leave one out cross-validation, then, our error says, okay, let's put back in this point that we didn't use. Okay, and we say, well, this is the actual point. It was 4, 4, and what did you predict? Okay, on this model, you predicted a 3, and so the error is a 1, and you square that, and you have a squared error of 1. All right, okay, and then we do this for we do this for all of the other things. Okay, so we're gonna take our total squared error. Okay, and so again, this is our original data. If I just keep observations 1, 2, and 4, so I throw away observation 3. Okay, so if I take away this observation, the best fitting line looks like this. Okay, and then I say, all right, let's throw back our validation point back in here and see how much error there is. Okay, and so here my squared error is 1.6531. All right, is this okay? And then so each observation, here's our original data points. We're going to take away observation 2. Okay, and then this is the best fitting line for the remaining 3 data points. And then we say, okay, well, what's the squared error there? And we get 1.6531. Same thing, all 4 data points. We take away this observation, the first observation, and this is the best fitting line for this. And we fit in that, and we get this squared error. And if I add all of these squared errors, this one is a squared error of 1. This has a squared error of 1.6531. If I add all those together, my total squared error is 5.306, and kind of the mean squared error for the cross-validation, leave one out cross-validation, is 1.326. Okay, and so this is just a value of estimating kind of our the error that might exist in some test data set for the linear model. Okay, and we would not just use this all by itself. Okay, there's not much value in cross-validation if you only fit one model and you get back a single number. Okay, because if you're only going to fit one model, that's the model you're going to use. There's no, I mean, I'm not sure what this is supposed to tell us. Okay, the power of cross-validation, and I didn't do this for this data set because I didn't want to have to draw all these graphs all over again. But the power comes in when we fit competing models. Okay, and I say, all right, what kind of cross-validation error did I get if I fit a linear model, and what kind of cross-validation error did I get if I fit a quadratic model, okay? And you would go through this process of kind of removing one at a time, okay, and figuring out these squared errors and getting kind of the mean of those things. And you'd say, okay, the total mean squared error from the cross-validation for the linear model was this number, and the total mean squared error for the quadratic model for cross-validation was a different number. And you would generally go with the one with the smaller cross-validation error rate, okay? Because the cross-validation error tells us how well our model is able to predict points that do exist in our data, but were not used when we trained the model, okay? So we didn't use these data points when we trained the model, but is it still able to predict actual values that exist in our data, right? Because the hope is that we have a model that's able to predict future observations that haven't even been observed yet, okay? But we have no idea what those future observations will look like. And so we're hoping those future observations look kind of like the data that we have in our current observed data pool, okay? But the problem is that if I use those currently observed data points in my pool, then it's really easy to overfit, right? It's really easy to just do whatever I can, keep adding variables to just make sure that I'm able to predict all the data points in my current data set perfectly, okay? But that feels like cheating, or that is cheating. And so what we do is we purposely say, okay, you don't get to see these data points. Train the best model you have over here and see how we do on the data points we didn't observe over here. Okay? Does that kind of make sense? All right, and so this is, I just drew all of these graphs to just get this single number here. But again, the value isn't coming from just this one number in of itself. Okay? The idea is you would get this number for one set of models, or for one model, and you would get a number derived the same way for a different model, and you would compare those cross-validation error rates, and you would pick the one with the lower cross-validation error. Okay? Luckily for us, you don't have to go through this manual process of fitting the model, making the prediction, taking the difference between the actual value and the predicted value, and the predicted value, and squaring it. Okay, you don't have to go through that process. R has the package boot, okay, and you can use this function called crossvalidation.glm, and it will figure out your leave one out cross-validation number. Okay, so over here we got this number 1.326531, and here you can get that number without having to fit 4 different lines and taking out this observation and this observation and this observation. You just say, all right, here's all of my data, x and t. We're going to fit t according to x, okay? And so you use GLM, but in this form it's the same thing as a linear model, right? We don't have like family binomial or anything like that. Okay, and then you ask for the leave one out cross-validation. That's stored under delta 1, okay? The other deltas are like adjusted things. Okay, and so this matches what we get. And again, we would do this to kind of compare the cross-validation error rate of one model versus another model. Not really use this just in of itself. Is that okay? All right. So there's a couple drawbacks. Okay. One is that if you have to fit n different models, one for each data point. So if you've got a big data set, you're fitting a lot of models. Okay, and this could be computationally very expensive. Okay, so that's a bummer there. Okay, and then another thing is the idea of, if your data set isn't super representative of the population, like if there's something weird going on, your cross-validation error will probably underestimate this number. Okay, this number might not be the most accurate thing if your data set isn't super estimate because if you only subtract out one data set, each of your data sets look very, very, very similar to each other, okay? So you run into a little bit of issues there. Okay, but this is a big issue, fitting n different models. If you got a data set with 100,000 observations, you don't want to have to fit 100,000 different models. That's stupid. Okay, so the alternative is to do k-fold cross-validation. Okay, and so k-fold just says instead of doing one observation at a time, let's divide our data into k different chunks. So you might do like 5 different chunks or 10 different chunks or something like that, okay? And then you use the same training and validation approach, okay, but on each of the different chunks, okay? So here, this would be 4-fold cross-validation, okay? So you take all of the data, you split it into 4 chunks, and you use chunks 2, 3, and 4 to train your data, and you validate on the first chunk, okay, or the first fold. And then at the second iteration, you use folds 1, 3, and 4, and you validate on fold 2, okay? And so on and so forth. And so now we only have to fit the model 4 times. And you're going to get a pretty good estimate this way. So if you've got something like 10,000 observations, you don't want to fit 10,000 models. Do like 10-fold cross-validation or 5-fold cross-validation, you only have to fit 5 or 10 models, okay? Okay, so here's our Olympic data, okay? And we've got 28 observations, and we've got year and time. And we can say, so this is what we've got. And we can ask, so here I'm going to do a 4-fold cross-validation, kind of a manual way, right? So we could easily do this in R using CVGLM, but I'm going to go ahead and illustrate this manually, right? Okay, and so first I'm going to shuffle up the numbers 1 through 28, okay? So I've just imagined a deck of cards 1 through 28, and I've shuffled them. And I'm going to take 7 cards and put them into set A, set 7 and set B, and set C and set D, okay? And so here it says, so this index 1 through 7, this is going to be just 7 random numbers from 1 through 28, and there's no overlap between sets A, B, C, and D, right? Is that okay? All right, so this is what I've got. I've got sets A, B, C, and D, and then, and so here's a little loop to do cross-validation, okay? Oh, this is, don't worry about that, okay? And okay, and we're going to keep track of the total squared errors. Okay, so we're going to fit a linear, quadratic, 3rd order, 4th order, 5th order, and just for fun, an 8th order polynomial. Okay, and so here's some code that I'm going to run, and this is just partial, but basically I'm going to take the validation index, and that's going to be sets double bracket I. Okay. And so for training, we're going to take our input data, subtract off the validation index, and subtract off the validation index for a training t. For the validation set, we use the validation index and whatnot, okay? And then so we've got my training set and my validation set, and I'm going to fit a linear model on t versus x on the training, okay? And then what do? I'm going to predict using this model I just fit on the validation set. Is that okay? So I'm just predicting this. And then to calculate the cross-validation error, I say, okay, take the true values, validation set the true values, and subtract off the values that I just predicted in the previous line, the t hat ones. Okay, so take that difference and square it, sum them up, and divide by n. And that's going to give us kind of our mean cross-validation error. Is that all right? Okay, and I do the same thing on the next slide. It kind of continues on. Whoops. Something got lost here. Okay. I don't know if you guys can read this, but basically I do the same thing as I did up here, but I'm going to fit a second order polynomial and use that model to make predictions. I'm going to fit a third order polynomial, use that model to make predictions, fit the fourth order polynomial, use that to make predictions, and so on and so forth. And each time I'm going to calculate how different were the predictions in the validation set from the predictions made for the validation set. How different were the actual data points and from their predictions. Okay, and I guess I'll show you the results on Wednesday, okay? Because we're out of time here. But we'll leave off there, and you know, I look forward to our class. I'll try to get your first homework assignment posted up already. There's going to be a lot of coding to do. It's just the nature of the 102 series, okay? All right, with that, we'll see you guys on Wednesday, and look forward to a great quarter.